All right, folks. Gonna run through quickly just a one-way ANOVA, just running the Omnibus test for this example that we just finished up with the screening with in the last video. Again, our data here are we're saying that we're running an experimental design looking at affective types of things, and we've got a video that is funny. Or is supposed to elicit positive emotion, but we're concerned and want to test empirically whether or not participants of different racial ethnic backgrounds find this video equally pleasant and emotionally arousing. So the handout that we're going to be using is our SPSS one-way ANOVA handout here. And so again, we're working with a one-way ANOVA with 3 levels to our factor. Okay, so gonna go pull up our data that we just finished screening. Again, as a recap, didn't find anything too concerning, at least with the preliminary screening. We have unequal sample sizes, 40 in our white non-Hispanic group and 20 in our other, so it's an unbalanced design, but distributions looked okay, at least in terms of distribution of sampling mean. We have a 0 to 8 scale. There's only so far a thing can be an outlier, but noticed 1 or 2 points in the screening that might be worth taking a look at. So we're feeling comfortable moving forward with our analyses. And so what we're going to do is we're going to go and execute this ANOVA. So we're going to go to Analyze, and we're going to go down to Compare Means One-Way ANOVA. Click on that, and we want to run our ANOVA model both with valence and arousal, with ethnicity as our factor. Okay, again, this is our factor. Functionally, what this model is going to do is it's going to look at the relation between ethnicity, or racial ethnic background, and response to this film. So one-way ANOVA with 1 factor, 1 IV, with 3 levels to that. Okay, so we're just going to run our Omnibus model here. So not going to worry about contrast or post hocs, but we're going to go through and we're going to click on options, and we're going to request descriptives. We're going to request our homogeneity of variance test, and then we're going to request this Welch's test. Remember, the Welch's test will give us a corrected test or an adjusted test in the case that we violate homogeneity of variance. Again, this is the one assumption that we didn't test in the previous screener because we get this when we run through and get our actual analyses. So we'll grab those, we'll hit continue, and then paste. So we've got our new syntax file here, and this is really all we need to do. So we'll go through, highlight that, and run it. And here's our output. Okay, so we've already screened these data, and so we have a good sense for what our mean standard deviations look like. But again, always want to double check this to make sure that nothing got turned around between your screening and the time that you went through and ran it. Again, we see our unbalanced design. Here's our means for emotional valence, means for arousal, 95% confidence intervals around our mean estimates, min max. So just want to go through and take a look at that and make sure things are similar to what you remembered them being. All right, next we see our homogeneity of variance test. This is going to tell us whether or not we violated a homogeneity of variance assumption. If we get a significant effect in our Levine's test, it would suggest that perhaps our sample, or that based on these data, there's reason to suspect that we may be drawing samples from populations that have different variances, which is going to be a violation of our basic ANOVA model. And so this is going to be particularly important given that we have an unbalanced design. It's not as unbalanced as it could be in many cases, but it's still worth taking a note. So as we're interpreting our Levine test, we see that for emotional valence, not a lot of evidence of reliable differences in our variances. We have a test that fails to meet criteria for statistical significance. semi-large cells, but again, based on this, we're not going to be too concerned about our Levine's test. But for emotional arousal, it looks like we do have potential possibility of populations with non-equal variances. If we take a look, we see that this is statistically significant, suggesting that at least one of our samples, or suggesting that at least one of our samples was drawn from a population having that has a variance in emotional arousal scores that's greater or less than the other groups. Now, remember, this is a variance test, and we've got standard deviations up here. But if we're looking at our emotional arousal, it looks like maybe our Black non-Hispanic participants may have more variability in their ratings of emotional arousal than perhaps the other groups. And so, again, because we have an unbalanced design and evidence of unequal variances, we're probably going to want to go through and see if we can get a corrected test on this. So this is definitely something that we would want to flag moving forward. Okay. So see that we have violation of homogeneity variance in one analysis, but not the other. Here, if we drop down and take a look at our ANOVA models, we've got our ANOVA model for valence and our ANOVA model for arousal. Here, just as we tabled in class, we have our sum of squares estimates, sum of squares between. So this is capturing variability in our effect. Remember, in ANOVA, when we're running ANOVAs, variability is just another term for differences. This is how we're qualifying differences. So we have our variability between, in our means between groups. We have our variability in scores within each group. Okay, remember our within group variance, or excuse me, our within group sum of squares. This is going to be also known as our sum of squares error. And this is going to be our total sum of squares. This is all the variability in the set together. So if we add this to this, this is what we'll get. Remember that our ANOVA model all adds up and works as it should. So here are sums of squares, our degrees of freedom, and then our mean square. Remember, in ANOVA, mean square just means variance, like a proper variance estimate. Here, we take our sum of squares between, or our sum of squares effect, divided by 2 is going to give us our mean squared between, or our mean squared effect. Here we take our within groups sum of squares divided by 96, gives us our mean squares within, or our mean squared error. This is going to be an important piece identifying this for moving forward and calculating some of the contrasts we'll do later. If I divide my mean square, some differences that I observed over differences that I would expect just based on random stuff, gives me my f-test and then my statistical significance here. Okay, so for our valence ratings, it looks like we've failed to reach criteria for statistical significance, and so we would fail to reject the null hypothesis and say that we did not have sufficient evidence to claim reliable differences in ratings of emotional valence across our different racial ethnic groups in this case. So didn't find anything, or didn't have evidence to make a claim here. But down here below, we have our test for emotional arousal. Same situation, sum of squares between, sum of squares within, sum of squares total. Our variance across groups, our variance within groups, and then if we divide our between by our within, or our between by our error, we get our f-test, and here it's marginal, right? But remember that when we went through and we ran our Levine's test, we found that we had a violation of this, right? And so we're concerned then with whether or not this is how we would interpret this effect, because one, we have unbalanced design, and two, we have evidence of violation of homogeneity of variance, and so we can't put a lot of confidence in this inference. Luckily, what we can do is we can go down through and we can take a look at our Welch's test. So if we go down and look at here, our robust test of equality of means. This is our Welch test. Here's our Welch statistic, degrees of freedom numerator, degrees of freedom denominator, and then our test of statistical significance. And here, our Welch test is saying that we are based on our reject, fail to reject rules. We would reject the null hypothesis and claim sufficient evidence for reliable differences in ratings of emotional arousal across my 3 different groups here. Okay, so again, as we're going through, want to see as a final check on our assumptions whether or not we violated homogeneity of variance. If we haven't, then we can go down through and just interpret our regular old ANOVA. But if we have, want to go down through and take a look at our corrected test, right? And so it looks like we have evidence for differences perhaps in ratings of emotional arousal, so the extent to which people are reporting being activated by this film stimuli that we've shown. Looks like there may be differences across different racial ethnic groups, but not so much in terms of overall pleasantness. But remember that we talked about in class, just because we violate our homogeneity of variance, we don't just ignore it and just drop down here, wanting to think about, based on these data that we've collected with sort of not huge samples, but sort of a big enough, at least from a statistical standpoint, to sort of get a beat on things. It looks like we may have greater levels of variability among our black non-Hispanic participants than our white non-Hispanic participants. Remember that if I'm talking about variability within a group, that's error, right? Because if the only thing that determined valence and arousal across these groups was the only thing that determined ratings of valence and arousal was group membership, if I had a perfect model, then all the scores would be the same. Everybody within a group would rate the film the exact same way. But we don't see that. We see differences within a group. That means there are other things going on. This could be systematic things. It could be random things. But what these data are telling us with this violation of homogeneity of variance is that not only do we see differences across groups in terms of their rating of emotional arousal, we also see differences in the variability, right? So again, if I'm looking at this, if I'm thinking about emotional arousal, I might hypothesize that my experimental stimuli is producing much more consistent ratings in this group as opposed to this group. There's more error in this group, right? And so even though our analyses are focusing on differences in means, this violation of our homogeneity of variance assumption may be an important thing to think about if I'm trying to understand sort of whether or not this is effective stimuli to be presenting across more diverse groups of individuals. Okay, so that goes through and takes us through our test. The only last thing we might want to do is calculate effect sizes. So if we go up to back to our handout, and I modified this a little bit, so this is just what was presented in the in our output. We could, for these analyses, calculate both eta squared and omega squared. Okay, remember that eta squared is a descriptive measure for these data, indicating the proportion of variability in our outcome that's attributable to our grouping variable. Okay, remember that eta squared is inflated. It's an overestimate of the population variance, so it does a nice job of saying in these data what proportion of variability in valence and arousal ratings is attributable to group membership. But in terms of being a population estimate, it's going to be too big. It's going to be inflated. This is where our omega statistic comes in. Our omega squared is going to be a better population estimate. It's still going to be inflated systematically, but less so than eta squared. Okay, so our value, remember that we're going to calculate eta squared and omega squared based on values that we pull from our ANOVA table. So here I've got hand calculations that you can take a look at. For eta squared, for valence, we're going to go through and we're going to take our sum of squares treat, or our sum of squares between, and divide it by our sum of squares total. And this is where we're going to get 0.043, suggesting that 4.3% of the variability in valence ratings in these data are attributable, can be accounted for by group membership. This is actually a medium-ish, or getting close to a medium-ish size effect. So even though we failed to reject the null hypothesis, even though we failed to find a statistically significant difference, it looks like our effect size suggests that maybe there's nothing there, right? So again, we want to take that into account. Our omega squared statistic. Now this is a little bit more complicated, but not too bad. What we're going to do is we're going to take our sum of squares treatment, or our sum of squares between. We're going to subtract k minus 1, that's the number of groups. So this is going to be 3 levels of our IV minus 1 times that times our mean squared error, right? So our mean squared error here, this is our average within group variance right here. Okay, we're going to take all that over our sum of squares total plus our mean squared error, and if we go through and we put that together, we end up getting omega squared of 0.023. Now, remember, our concern with eta squared is that it's going to be an inflated test statistic. It's going to be a positively biased estimate of the population parameter, and we can see that our eta squared is bigger than our omega squared, right? So for these data, we would say that about 4.3% of the total variability in valence ratings is attributable to our grouping factor. Here, we would say our omega squared value, we might interpret this as saying, based on these data, we would estimate somewhere about 2.3% of the variability in valence ratings in response to this film are attributable to grouping membership here in the population, right? So this is going to be our population estimate, and this is going to be a more descriptive piece. Same thing with arousal, taking sum of squares between over sum of squares total. Again, this is what systematic differences that we observed over the total variability, and so we see that for these data, our grouping factor accounts for about 5.8% of the variability, total variability in ratings of emotional arousal. Again, if we go down through calculate omega squared, get a smaller value, we're taking our sum of squares treatment, or sum of squares between, minus 3 minus 1, or k minus 1 is going to be 2, times our mean squared error right here, all over sum of squares total plus mean squared error. It's going to give us a value of 0.038, and this suggests we might interpret this as in the population, this hypothetical population of individuals of white, Hispanic, white non-Hispanic, black non-Hispanic, and our terrible other group, which is sort of our catch-all, at least in this study, which doesn't make it a good study. But we're saying within the population, about 3.8% of the variability in arousal ratings we would expect to be attributable to group membership. Okay, so this is our Omnibus test. Omnibus test is pretty easy, straightforward stuff. Again, big takeaways here. Violation of homogeneity of variance. Here, I'll go through and open up this. Okay, violation of homogeneity of variance for one outcome but not the other. This maybe being of a little more concern given the unequal sample sizes. Based on these data, not a lot of evidence suggesting systematic or reliable differences across ratings of valence by group. But again, looking at our Welch test down here, having sufficient evidence in our corrected statistic to claim evidence for reliable differences in ratings of emotional arousal across our different groups, and then going through and quantifying the magnitude of that effect with our eta squared and omega squared statistics. So that's that. Let me know if you have questions, and we'll pick up with this in class on Wednesday. All right.